right, so it says write the given expression as an algebraic expression in X. Okay. Now you might have had sine, you might have had cosine here as the inverse function. I don't think you usually get anything. Anybody have like a tangent in there? It shouldn't really matter. You put anything in there you want to. Secant, cosecant, tangent, cotangent. The setup is the same. It's just whether you have the particular sides that accompany a sine or cosine or tangent in the correct orders. Okay. What we're going to do first is realize that when we are provided with the inverse function, okay, first of all, this is a nested set of functions. This is ultimately, if you were to work your way backwards, it's a composite function, okay, like an f of g of x, okay. With those and evaluating those, we work from the innermost function outward. So I'm going to concentrate on cosine inverse of x. But I have to understand a little bit of the structure here of the cosine inverse and what we mean by that function having an input. That input right there for cosine inverse is a ratio of an adjacent side divided by a hypotenuse, right? If it was sine, it'd be opposite and hypotenuse. If it was tangent, it'd be opposite and adjacent. Secant, cosecant, cotangent, their respective sides divided by one another, right? So that's where it doesn't really matter what that trig function is, as long as you know that tangent is opposite over adjacent, or cotangent is adjacent divided by opposite. Okay. What this does for us then, the output, so that the input is a ratio, the output is an angle. Okay. So with composite functions, we got to figure out what is that output. Okay. Well, if I draw a picture of what is going on here when we say cosine inverse of x, that means that the adjacent side is x and the hypotenuse is 1. This is a ratio x over 1, right? That then produces, through the Pythagorean theorem, this side here to be 1 minus x squared. Okay? But the output is that angle right there. That's the theta, whatever variable you want to use. That is what this thing is spitting out to us. Okay? And it's spitting it out to us attached to this triangle with the information that is inside that triangle. So what I'm going to do is I'm going to reevaluate this then. I'm going to rewrite this as now tangent of 2. This thing gave me theta of this triangle. So now that's a tangent double angle formula. And what that turns into is 2 tangent of thetas divided by 1 minus tangent squared theta. And that's going to be a formula that I provide you with. Okay. It's generated from knowing what tangent of theta plus theta looks like and go through that process. Or knowing what sine, if you didn't remember that, if you don't have a reference sheet, maybe you know what sine of 2 theta is. Maybe you know what cosine of 2 theta is, and you can go through kind of the algebra there that generates this formula. So now I'm just going to have to, because now I know what theta is, and I look at my picture, and I've got all the information needed for the tangent of theta. Now I'm just going to substitute. So we have 2. Now tangent of theta would be opposite over adjacent, right? So it would be root 1 minus x squared all over x. That would be the numerator. Denominator is going to be 1 minus tangent squared. So it's going to be the root 1 minus x squared over x I'm going to square that. The top becomes 2 roots 1 minus x squared all over x. The bottom fraction. I want to condense these. Okay, so first thing I'm going to do is just apply this power of 2. So when I apply that power of 2, that's going to cancel, right? It's going to leave me this to be squared. So if I wanted to do the subtraction then of this stuff, I'm going to have to write this as x squared over x squared, right? So what I get is x squared, then this minus sign, and then this radicand of 1 minus x squared, all over then x squared. That's what that bottom fraction is going to evaluate to, okay? Now I can do a little bit more with that. That's I did x squared. Oh, I'm sorry. This is minus. This ends up being a quantity, doesn't it? So I should do that. So then it's x squared minus 1 minus a negative x squared, so that becomes 2x squared, right? So I've got 2x squared minus 1 over x. And then up top, I got 2 root 1 minus x squared over x. We should be able to multiply by reciprocals, right? And I get x over 2x squared minus 1. So now multiplying all that out, I'll write the final down here in red. It'd be 2 times x times root 1 minus x squared. Obviously, the x's drop out, right? So I don't really need, sorry for putting that x in, I don't need that x. And then on the bottom, I'm going to have 2x squared minus 1. And that should be my solution. If I mess that up, okay, I'm sorry. So you're right, that's an x squared there. So I do keep an x up there. So that x squared and that x, one of them up here is going to cancel out with that one, leaving me still just an x in the numerator. So 2x times root 1 minus x squared all over 2x squared minus 1. Let's just double check. 2x root 2x squared minus 1. Okay. Now what that means to us then, guys, let's kind of look at this. You can either look at it graphically. I like to look at it through evaluating on something like Desmos. Or I want to create a slider here. So I'm going to go tangent of 2, and then cosine inverse of, I'm just going to put just some variable here, r. Doesn't really matter. It can be r, s, t, whatever you want to use. Anything, but don't use x, because it's not going to allow you to create a slider then with x. And then I'm going to type in what we just came up with. So it's 2x, which would be x being r now. Square root of, what was it, 1 minus r squared. And then on the bottom, we're going to have, is it 2r squared minus 1? Okay. Now, I'm just going to make sure, so the arc cosine has to be evaluated at r, okay? Meaning the domain of arc cosine has to exist. You may remember the domain for the arc cosine. Maybe if I put in some of these values, you start to see we've got undefined things occurring, right? Okay. If I were, let's just kind of do this real quick. Arc cosine of x, look at the graph. The domain is -1 to 1, right? Okay. So that's the only thing that my slider needs to be defined for. Otherwise, I'm going to get undefined solutions. And now here's the argument. if I make that slider change, are those two things, no matter what I substitute, are these two quantities always the same? So we've got the correct version. And what's nice about that is that it just got rid of the trig function, right? Okay. There will be times in a calculus course where you want to integrate something or differentiate something, and there's a trig function existing, and it's hard. So if we can get rid of that trig function and rewrite it in terms of just x, that makes it a little bit easier. All right, so that's a procedure that we'll come back for a application use later on. Some of you, so last class, this was a sign. Anybody get the sign? So there's additive algebra when the sign is present. So let's just do an example where this thing here is sine inverse. Again, just working with that innermost function. We're going to draw a picture. Okay, so it's going to produce this theta. But now sine is opposite over hypotenuse, right? Now it gives me that distance to be 1 minus x squared. Now when I go tangent of the 2 theta that this is producing, because that turns into theta, if I go 2 tangent theta over 1 minus tangent squared theta, we have 2. Now tangent theta would be opposite over adjacent, so it would be x over root 1 minus x squared, right? And then on the bottom, it's going to be 1 minus x over root 1 minus x squared squared. Okay. Top turns into 2x over root 1 minus x squared. The bottom, let's just kind of mess around with this a little bit. If I run this power of 2 through here, that's going to become x squared, right? And this is going to disappear, right? Okay. And then if I want to actually do the subtraction, I need a 1 minus x squared as that denominator. 1 minus x squared as that denominator. So now when I multiply that through, I get 1 minus x squared times 1. So it's just going to give me that, 1 minus x squared. But then it's minus x squared, right? So that's going to give me 1 minus 2x squareds over 1 minus x squared. Is that all right? Take its reciprocal. And now you get up top 2x. Now I'm not going to multiply this out, and a lot of times, guys, I just think foreshadowing a little bit helps you realize why not to multiply that numerator out. Because if I were to foreshadow what I'm going to do here in a little bit, when I multiply that square root 1 minus x squared by 1 minus 2x squared, am I going to have a radical in the denominator? How do you get radicals out of the denominator? You rationalize, right? You multiply by what that radical is in the denominator, right? And when you do that, you're going to be left with just the radicand of that radical. Well, the radicand of that radical is 1 minus x squared, right? Well, if I leave the 1 minus x squared in the numerator, and then when I rationalize the denominator, it's going to have a 1 minus x squared in the denominator. What's going to happen with those two things? They're going to cancel. But if I multiply that 2x through that numerator right now, I'm not going to recognize that there should be cancellation occurring. Okay? So when we finish this, when we get down to that point, kind of rehash that and talk about it again. But that's going to give me, when I multiply here, it's going to be square root of 1 minus x squared there. Now, we don't like that, so this is where we rationalize. So we'll multiply by the square root of 1 minus x squared, and up here, 1 minus the square, or 1 minus x squared. Now, multiplying that, again, I'm not going to multiply anything. I'm just going to do the implied multiplication. Okay? On the bottom, again, just do the implied multiplication. If I'm going to multiply these three things, because that's a quantity times a quantity times a quantity. Can I take those two, multiply them together? And that's the thing that happens here is those two right there become 1 minus x squared. And if I would have multiplied this numerator out here, I would not have seen that 1 minus x squared canceling with that one. And that's a process of just kind of knowing, I guess, that I've seen enough things like that to not FOIL out. Okay? If you get in a situation that you're stuck and say, I don't know whether to FOIL out or not to FOIL out, don't. Okay? Just do all the implied multiplication. See if things cancel, and if things don't cancel, then multiply. Does that make sense? Okay? But if you multiply out first, every single time that cancellation is going to occur, you're not going to recognize it. Okay? So I think that's a very, very important thing to recognize if our overall goal is to simplify these as far as possible. Okay? Now, if we were to insert that into Desmos, so we had 2r square root of 1 minus r squared over, now this becomes 1 minus 2r squared. This would have been arc sine of r. Now hopefully we remember this, but arc sine has the same domain. So negative 1 of 1 is fine on my slider. And now we see those two things evaluate the same way at all those values of r. Okay? Okay. When you're doing, and this is this won't always work with these types of problems because there's all types of different things we can do with this. We won't always get them even where they're defined to be the same thing. They're undefined in the same locations of R. That won't always be the case. Why is that happening here? We'll take 5.3, put it in here. That's 25 something, right? Okay, or over 25. 1 minus that's going to be a negative number, right? You can take square root of a negative number. That's why it's undefined there. That won't always be it. If a radical did not exist here, this could probably evaluate. Okay, so just be cautious of that type of thing later on. All right. Any other questions on that assignment, Femi? 18. Okay, final solutions of the given equation. Enter your answers in comma separated, let k be an integer, 2 decimal places where appropriate. All right, so did you have, what were your numbers? Okay, so let's go 5, cosine theta plus 1, 5, cosine theta plus 1. All right, so the first thing we're going to do is subtract 1 from both sides, right? So 5 cosine theta is equal to negative 1. Now divide both sides by 5. All right, so now, with this situation, we don't know what negative 1/5 is or where negative 1/5 is on the unit circle, right? So here we have to grab our calculator. And I believe it's set in radians, right? So let's just kind of work directly with our calculator in that mode. Let me just do it on Desmos. I get tired of TI-83, the way it's got to, I can't use my keyboard. All right, so if we are in radians, we're going to go arc cosine of negative 1/5. Okay, and that gives me 1.772. Okay, now here's the thing: that 1.772. This is 1.57 radians. So 1.772 is going to be an angle. That's terrible. It's going to be an angle over here in that second quadrant, right? So that is that first theta that we're interested in, okay? Now, the other place that cosine is negative would be down here, right? Okay, that would be the terminating ray. But the angle for that would be that big. So we have to figure out a way of figuring this out, okay? You can do one of two things, okay? Or maybe even multiple things, I don't know. You know that this is pi here, right? Does that mean that this angle here, that blue angle, is going to be 1.77 subtracted away from pi? Does that make sense? Okay, so if I did that, I went pi minus, just so I get a positive result. I want to go in that order. Yeah, you could do either. You could do arc cosine negative 1/5 minus pi and put in an absolute value. That'd be fine. But I want this angle here to be in radians to be positive, right? Okay, so that's why I did that order. Now, the reason I didn't just click this and copy it is I wanted the exact value. Okay, so there's no rounding in this. Because I'm going to take that number, and what am I going to do to that? So that number is this one here, right? That needs to be cut and pasted right there. Does that make sense? So how do I get this blue angle from here all the way to there? What should I add to this amount? If I went from here, what is that green angle right there? Pi, right? And I now know that this angle here is the 1.36 number, right? What can I do with those two to get that blue angle that I'm actually interested in? Add pi. So plus pi, that should give me my other solution. Okay? Now think about what we really did there. We took arc cosine negative 1/5 and took pi plus pi. What's pi plus pi? 2 pi, right? We took 2 pi minus arc cosine negative 1/5, right? That hopefully that makes sense visually, because if we were to look at that first angle we got, that's 1.77 right there, right? Radians. If I look at that angle right there, that is negative 1.77 radians, correct? Does that make sense? Let's put ourselves, so we don't like writing that as a negative radian. So I put myself there and say, how do I go from there and get all the way back to it? I take negative 1.77 and add 2 pi to it, right? Isn't that what this is doing? If I take those away, I give you negative 1.77. Add 2 pi to it, 4.5. Okay? So there's a couple different ways of kind of viewing that or working with that. I think both approaches there are really the same thing if you sit down and kind of analyze it. Does that help? Any others? Gives you a graph? Yes. Okay, so that graph, guys, the only purpose for that graph, this is stupid that they give this to you. I don't know that it's stupid to give it to you, but I think it's stupid the way they direct you in the question. Because you look at that and you think, well, I'm supposed to get these decimal places off that graph. That's not going to happen, right? So go to GeoGebra, go to Desmos, go to TI-83, 84, something like that. Or just go by hand. Okay, so the ultimate picture here is to tell you should have 6 solutions. 2 of them are negative, 4 of them are positive. Okay? But then if I go, so if I'm doing this by hand, I got sine, it'd be sine inverse of 0.6 is equal to x, right? So I'm going to grab my calculator and go sine inverse of 0.6. It gives me that number right there. That's one of our solutions, correct? 0.6435 right there. Now sine is also positive in what quadrant? Okay, so this 0.6 over here as well, right? So then I would take pi minus arc sine of 0.6. So it gives me that. That's another solution. Those 2 solutions right there. All right, does that make sense? Those correspond to these here. All right, everybody? Those are the 2 solutions that you're going to find. Now, how does that one and that one relate? Are they the same point but in a different cycle? Okay, so with the sine function, what is that period? 2 pi. So can I take this number here and add 2 pi to it? Okay, so if I go arc sine of 0.6 and add 2 pi, that should give me this number right here. Okay. Now how does this number here and that one, how do they relate? Minus 2 pi. Okay, so then by minus 2 pi, I get negative 5.639, which is that one there. Okay, does that make sense to everybody? So then the other one that I haven't dealt with yet is this one here. That one was this solution, correct? Okay, so to get this one over here that corresponds to it, what do I add? 2 pi. So there's one of my solutions. And how do I get the other one? Subtract 2 pi. Okay. We did this in the last class. But I'm just going to show you what we did there with this calculator. All we did, we took sine of x. I don't want to spend a whole lot of time doing this because we're going to run out of time with what I want to show. But this would be 0.6, right? Then if you read the directions, it says it wants you to be in a window that is between negative 3 pi and 3 pi. So I make my x minimum negative 3 pi, make my x maximum 3 pi. I went my scale by pi. My max and mins for my y, which is bigger than 1 and negative 1. And I graph it. And that thing right there is exactly the same graphing that they gave you in the image. Does that make sense? But now, with this on my TI-83 or 84, can I go second calc, go down to intersect, which is 5. And now let's say I want to find one of these. Let's find this first one all the way to the left. So I just take my cursor close to where they intersect on the first curve, hit enter. It jumps it to the second curve. Just make sure it's close to the intersection again. Hit enter. Then hit enter a third time when it says guess. And there's one of your solutions. Does that make sense? And then you can just repeat that process for all of those solutions. All right. I actually think, that's fast, but and I'm allowing you to use this. What if I did this? Sine of x, 0.6. I got to put y equals 0.6. See what happens right there when I click to give me those solutions. Now, I don't know how to, because I don't use Desmos enough. I don't know how to adjust that to get more decimal places. I don't know if you can, but that is another way. That's a quick way of getting those solutions. Okay. I don't know if there's a setting somewhere to adjust.
You have to zoom in real far, and it only shows up to 4 decimal places, including the whole number at the beginning, so you can't get all the answers.
Huh. That seems to be kind of dumb. I'll do some there's got to. I mean this is a pretty powerful graph. There's got to be a way to change it. I'll do some research and see if there's a setting somewhere. Because there's a lot of hidden stuff inside here that it doesn't inform you until you start just accidentally typing stuff in and realize that it's there. So yes, Femi. Yeah, I don't want to do one of them today. I want to do one right now. When we have something like 2, and we'll do a lot more of these tomorrow. Is that assignment due tomorrow? Thursday? Okay. Okay. So we get something like this. These are some questions that exist in the end of that homework assignment, 7-5. The 3 theta is the issue here. Okay. If you remember anything about these functions, when I have sine of, let's just say n times x, create a slider for n. Let's go by ones here. And if I look on the interval between, I want to go from 0, I want to include 0, and I want to exclude 2 pi. Okay, so we got solid lines, dotted lines there. If I look at this, and I just want to look at let's just say x-intercepts. There are 2 x-intercepts here, right? Again, not including this one, because it's on that dotted line. If I make n go to 2, see how it compresses that curve? And now you have 1, 2, 3, 4 solutions. So originally it was sine of 1x, you had 2, now you double it, right? If I go sine of 3x, how many solutions do I have? 1, 2, 3, 4, 5, 6. I tripled them. How many should I have now? If n is 4, should have 8, right? If n is 5, I should have 10. Okay? We have to have a process that takes from those 2 to get to those 4, goes from those 2 to get those 6, and that's kind of what I want to show here. First thing you're going to do, guys, you're going to solve this just like you normally do. You're going to add 1 to both sides, divide by 2, you get sine of 3 theta is equal to 1/2. Then you're going to inverse, okay? So you're going to ask the question, when does sine, and I'm just going to write 3 theta here, you write whatever your argument is, 1 theta, 2 theta, 3 theta, 1/2 theta, whatever, doesn't matter, okay? When is sine equal to 1/2? Give it to me in radians. Pi over 6. When's the other time? 5 pi over 6. Okay? Now, what we want to do here is we want to find all 6 solutions that occur. Okay? So the best way of doing that is to now create those infinite equations. So add 2 pi k here and add 2 pi k there. Does that make sense? So that's the second step. The third step is now solve for theta. I'm going to solve for theta. I'm going to divide by what? 3. Now, I'm always going to multiply by 1/3. Because that's going to now give me pi over 18 plus 2 pi over 3 times k. This theta here is going to give me 5 pi over 18 plus 2 pi over 3 times k. Now what we do is that we're going to let k move from 0. We always start at k being 0. And then we let it be 1. And then we let it be 2. And we keep going until we have that many k values being listed. So I've got 3 k values being listed, right? Okay. A lot of times they'll call that n. and they'll say let k go from 0 to n minus 1. Okay? But now if k is 0, isn't this solution pi over 18? If k is 1, so now I'm adding 2 pi over 3, which would be actually 12 pi over 18. So this gives me 13 pi over 18. And now k is 2. Now here's the thing. I'm adding the same common difference. I really have basically an arithmetic sequence here. So what was the common difference between these two? 12 pi over 18, right? So I'm going to add that same 12 pi over 18 and you get 25 pi over 18. Down here you do the same thing. We'll start with this again tomorrow.
That literally.
Subtraction.
Absolutely. They're doing
So we'll start that example tomorrow. I'm going to send out a practice test here in a little bit.